Okay, let's go and get started for the day. Today we're going to be looking at a continuation of what we did last time. And in this case, what we're looking at is, this is class 15. We're going to be looking at information transfer and the OSI model. And as a quick note of something you should be aware of, after this lecture, you should probably look for the quiz that's on the course site. So make sure to look for that and take that. Okay, so information transfer and the OSI model. Last time, you'll remember, we looked at the concepts of packets and protocols. And as a reminder, a packet is sort of a block of data. And in that block of data, you had a data portion, which we called the payload. But there was also a header placed on the front that maybe described a sequence number, maybe had addressing information, maybe had other things about that payload, including the length. And then we also had this check value or CRC or checksum or something that was the redundancy for checking to see if there was some sort of a corruption or error or noise that happened while the packet was being transferred. And that check value, we talked about that a few lectures ago. All right, a protocol is the set of rules that say, well, what do we do with those packets? How are they created? How are they transferred? What happens when one is detected as bad? Do we re-request it? How many times do we re-request it? How do we start up the session? How do we close down the session? And so forth. And we ended by discussing some real-world protocols. And we had mentioned how they can often be layered on top of each other or layered in their kind of design themselves. So that's what we're going to focus on today, is the layering of packets. And a couple examples of that before we move too much further here is if you look at HTTP, which if you, or HTTPS, which is really just a secure version of HTTP, that's a protocol that uses, that's the protocol that web pages are transferred using, but they sit on top of TCP/IP, which is like the communication language of the internet. So when you have a IP address, like you have for your computer, when you log into a Wi-Fi, it gives you an IP address to use, or you have an IP address of a server, like 146.85.1.1 or whatever, 206.21.94.6, whatever those IP addresses are. When you have an IP address, that is the language of the internet, but on top of that sits HTTP. And if we look at TCP/IP, well, that's a suite of protocols. It's really two separate layers there. TCP sits on top of IP. TCP, and we're going to look at these in detail next class, but TCP sits on top of IP. And those themselves use a lower level network protocol, such as Ethernet or wireless Ethernet, Wi-Fi. And Ethernet is a low-level protocol that puts data onto the physical network. So you can see how these are layered on top of each other. HTTP for web pages at the top, sitting on top of TCP, which is responsible for making sure that the sequence of packets gets sent through correctly, sitting on top of IP, which deals with the individual packets and their addressing and routing, sitting on top of Ethernet, which gets the data onto the physical network to the next node on that network, and to be routed to the end destination with the IP stuff wrapped inside of the Ethernet packet. Inside of that is TCP and HTTP ultimately at the end of that. So that kind of layering makes sense. So the idea here is that each of those protocols has a different set of rules and has a completely different kind of packet and message structure. They also all have a different role to play that requires different functionality for each. So going back for a second, notice this just deals with web page content. This deals with sequencing of data in a streamed or maybe I shouldn't say streamed, in a sequenced connection to make sure the packets are received in the right order and none are missing. IP doesn't care about either of those things. It just cares about the addressing and the routing of it. And then Ethernet is the low level, getting the data onto the physical network that might be a wire, could be Wi-Fi, but there's a different kind of encoding for each of those methods. Now, how can they work together cooperatively? Well, the answer to that is they need to have some organizational structure that allows them to be used cooperatively or used together. And the answer to that is what we would call a layered approach. And that layered approach is allows them to, rather than having parts of them all mixed together, you have a nice defined area where this is the IP part, this is the TCP part, this is how HTTP is, this is where the data for it lives, this is where Ethernet is. And essentially, the idea for that is a while ago, it became clear that there were going to be different types of data going across different types of network. And you want web pages to be able to be accessible across different kinds of network, and you can see that as you use it. For example, you can bring up a web page on your smartphone. You can bring up a web page on your PC. You could bring up a web page on different kinds of PCs. You could have a program contact web page. There's just all kinds of ways that you might want to access that with HTTP data. It could be Wi-Fi. It could be a wired connection. It could be a dial-up modem. It could be a GSM connection, like a telephone, a smartphone. So there's a whole lot of those different low-level things. But HTTP, it's the same kind of data from the same internet. So we have to have a way to get TCP and IP to work over all those different physical things. And then we have to have a different way to have the web pages use TCP IP using that low-level thing. And so the idea was there needs to be this layered approach to that. And so what they did is they came up with a standard for how, not an individual protocol, but a standard for how you should design a communication system. And what they came up with is this thing that's called the Open Systems Interconnection Model, or sometimes it's called Open Systems Interconnect Model. But it's what's called the OSI model. And the OSI model is it's like a standard for how you make networking standards. So the idea there is a little bit of history. In the late 70s, computer networks were proprietary things. And they were implemented in these vastly different manners. And it made it difficult for them to communicate with each other. So you could have data on one network, but you couldn't get it onto another one. So the International Standards Organization, they set out to define this hierarchical model that would allow it to be easier to have data of one type on one kind of network than peacefully coexist on a different kind of network. And the idea was, as long as they adhered to some standard, then it would be easy to unwrap part and rewrap it in the other networks. In other words, you have this data part like HTTP wrapped inside of an Ethernet packet. If you do that right, you could unwrap the Ethernet part and wrap it in a different kind of wrapper for a different kind of physical interface. And you can see that at work when you connect to something over your smartphone. You connect over a smartphone that uses this GSM low-level protocol to talk to the cell towers that then convert that into some sort of wired connection and wrap it in the packet for that wired connection. And that could be fiber optic, it could be Ethernet of some sort, it could be some sort of OC3 or whatever. It could be any kind of wired connection at that point. It could even be another wireless connection, like a microwave connection to somewhere. But the cool thing is, if we followed this OSI model where it kind of wraps things in layers, we just peel off the layer we don't need anymore, wrap it in the new layer, send it on its way without touching the stuff inside. All right, so what the International Standards Organization came up with was this OSI model. And the OSI model kind of has these two major components to it. The first one is this kind of abstract model that they call the basic reference model or the 7-layer model. And then it also has a set of protocols associated with it. And the part that you mostly hear about is the 7-layer model. We're going to talk about that here in just a second. So the OSI model basically said when you create a networking system, you divide it into layers. And those layers are separated into kind of different types of functionality at each of the layers. And the idea is each layer only interacts with the layer immediately beneath it and provides facilities to the layers that are immediately above them. So in other words, rather than having the layers like having this really complicated mix of this functionality is here, and then we have some there, and then we skip back to stuff that's like that, and then we have some down here. And having all that data kind of jumbled together, the idea is you put it into this nice stratified layer approach. So the top thing deals with the thing below it. That thing deals with providing services to the thing above and accessing the thing below that. And so the idea there is that's what is going to allow you for this kind of modular networking architecture. And it's going to also allow you to do that kind of unwrapping and rewrapping of parts as we need to, depending on what kind of dissimilar networks and what kind of things that data is traveling across. And so the idea is each layer on a host would interact with the same entity on the remote machine. So in other words, for example, the application layer interacts with the application layer on the other end. And it does that by wrapping that inside of those packets. Let's take a look at some of the layers here, and then that'll make a little more sense. Okay, so the 7 layers of the OSI model basically look like this. It's divided into 2 main categories, the host layers and the media layers. And the host layers are things that are kind of software-based on the machine. The media layers are things that deal with the networking itself. And so at the very top here, what they call layer 7, is the application layer. So that's a program running, and the idea there, that's the network process that's used by some application. So let's say you have a network game. That might be up here at the top. So that's a game using some sort of network services. Below that, we have this presentation layer. And the presentation layer would be something like the data representation. What's the endianness of an integer data, the piece of data that's being sent? Maybe on some machines it needs to be, the bytes need to be swapped. Maybe some of them, maybe it's big endian or little endian. We need to handle that so it presents the data correctly to the application as expected. Another thing that winds up in presentation layer a lot is kind of encryption. If you want to encrypt the data, you would take the application, it would pass it through this encryption engine, it would encrypt the data, and then it would pass that data below to the next layer down, which this would be what's called the session layer. And the session layer is designed to deal with things like a connection-oriented protocol, where something has to initiate the connection, you then exchange data, and then you close the connection when you're done. So in that case, we would have, for example, in our game, let's say that we wanted to encrypt the data that goes across, and we want to create a connection so they're connected to the server. That would be session layer stuff. That doesn't have anything to do with encrypting the data. It has to do with how do we create the session, how do we make sure that no packets are duplicated, how do we make sure that any of them that are missing are retransmitted, how do we make sure that they're not received in the wrong order so that we get a nice transparent stream of data on a session. Now the next one down below that is the transport layer. And what the transport layer deals with is kind of the end-to-end connections and reliability. And really, the session layer is responsible for initiating a session and closing the session. The transport layer is responsible for making sure no packets are lost and no packets are duplicated. And then below that, we have the network layer, which adds the addressing information, kind of the logical addressing and routing data. And then below that, the data link, which is the physical addressing, putting addresses on it to get it onto the physical network. And then below that is the physical layer, where we're actually putting the stuff onto the wires. Now, there are a couple of other layers that you hear referenced that aren't part of the official model. That layer 0 essentially is referring to sometimes jokingly referring to the electrons or the electric service. So for example, if somebody says there's a layer 0 problem, that some IT person says, oh, it was a layer 0 problem, that usually means something along the lines of that the power went out or somebody unplugged the server or something like that. Also, a layer 8 problem is also used in a joking way to refer to the end user problem. So it's not a problem with anything in this. It's like, oh, I discovered the problem on our network. It's a layer 8 problem. that means there's an idiot user that didn't know what they were doing, or they did something wrong and screwed something up. And that's why it wasn't working anymore. So that's somebody using the application incorrectly. Notice those are not official layers, but you'll hear sometimes those referred to. So if somebody says that to you, you'll know what those are referring to. All right, so let's dig through this a little more detail through each of the layers. So the physical layer, and I'm going to go through those backwards from the way I did here. So here I started with the application and worked down to the physical. And what's going to happen is that data is going to cross to some other entity, and it's going to go back up through that stack. And you'll also hear it referred to as a network stack. And the reason it's called a stack is because these things are kind of piled on top of each other, stacked up on top of each other like this. Okay, so let's go through these one at a time from the bottom, working our way up. So layer one, the physical layer. So that defines the electrical and physical characteristics or specifications for the devices. So that might include the layout of the pins, voltage levels, acceptable line or cable lengths, acceptable cable communication, capacitances, and things related to that. So if you have an Ethernet port on your machine, that's part of that physical layer process. That's the actual, you have a network card in your laptop, or maybe not a card, but a network interface in your laptop, or a network card in your PC, or a chipset on your motherboard. That chipset is responsible for this physical layer stuff going on here. How does the line encode the data? And we've seen a lot of that in the stuff we've done previously in this class with encoding the data ourselves. This is kind of like the physical layer would be the specification for how do you encode the data. Is it Manchester encoding, or is it something else? So that is physical layer stuff. And that things like fall into that category to be like hubs and repeaters and network adapters are kind of physical layer devices that deal with getting things onto wires and off of the wires. Hubs and repeaters might also work at higher levels as well, but they're still physical devices that physically encode the data onto wires, or in the case of a Wi-Fi access point, reading the stuff out of the radio frequency waves and putting it out, transmitting things in that, and then probably also connecting to a wire. Now, moving on with that, the major functions of the physical layer, they are basically establishing some sort of connection to the physical medium, meaning the actual physical, like wires themselves. And it also includes termination. How do you disconnect from that? How do you connect to that? It also involves how that resource is shared with multiple users. So for example, in Wi-Fi, you have multiple people talking to a Wi-Fi access point at the same time. How do we deal with that? How do you deal with contention resolution? In other words, two people try to transmit a packet at the same time. Or flow control. How do you say, hey, hold off a second, I'm busy? How do you share that network with multiple users? In the case of Ethernet, it might be like a standard 100 base T Ethernet. It might be, how do you deal with all of these packets coming from multiple machines simultaneously? How do you deal with that? It also deals with modulation and conversion between the representation of digital data in that equipment and the signals that are transmitted over that channel. In other words, how do you get the data, the binary data, ones and zeros, onto this physical thing as electrons or radio frequency transmissions, or in the case of fiber optics, light. So those are signals operating over that physical cabling. Could be copper, could be fiber optic, could be radio link. There's a lot of different ways that could be sent. But the idea there is, what is the modulation process? How do you encode the data on that channel? That's part of the physical layer as well. Now, once you have that physical layer built, then you can build things on top of that or communicate on top of that, which we're going to see in just a second. But a couple things that work at the physical layer, which you may have seen or we've talked about in the class before, would be things like Ethernet. Although really Ethernet also includes data link layer stuff with it, with addressing. We'll see that here when we get to layer 2. But also the SCSI, or Small Computer Systems Interface, which was a standard for connecting hard drives and things like that. RS-232, Token Ring, FDDI, which is a fiber optic interface. The 802.11 for wireless networking, Bluetooth, Zigbee, 802.14, and so forth. These are all have physical aspects to them. These are wireless down here. This is optical here. These are wired up here. Now, data link layer. The data link layer provides this means of transferring data between the network entities. So it's not quite just how do you modulate the ones and zeros onto the wire. This is how do I address those physical entities. So how do I say, here's a block of data, and I want to send it to this other physical machine over here. And the idea there, it might have some error correction built into that, but notice this sits on top of the physical layer. We're going to use that physical modulation scheme, but now this is how we create a packet, or maybe we call it a frame, that gets sent and verified to some other node on the network that has a physical address associated with it. So the best known example of that is Ethernet, which, as I said earlier, combines both the kind of physical layer and the data link layer into this kind of one Ethernet standard that they have. So it has both the modulation and how do you make the packets that go onto that go from place to place. Now, another thing about that is, I don't know why it says internet. Let me fix that real quick. All right, so for the internet, that layer may be thought of as split into the kind of media access layer and the 802.2 logical link control layer. Actually, that should say Ethernet. I don't know what happened there. All right, there we go. Now, the bits from the physical layer are organized into chunks of data known as frames, and then those are transmitted. That frame goes from one machine to another machine over that physical interface, modulated in that way. And that kind of layer is where things like bridges and network switches operate. So when you have a network switch, like you look at the data closet or a server room where there's a big panel with a bunch of things going into a network switch and the lights are flashing, those are receiving those frames that are organized as Ethernet frames, and that's routing them or sending them to the connection where it knows that MAC address of the receiving machine is. And MAC addresses are kind of the media access control address, and those are associated with every Ethernet device. So those are also called the hardware address of those devices. They're unique. They're set at the factory. So every device has that unique ID. So you can say if my this wired machine wants to talk to this other wired one, it puts in the MAC address as part of the structure of this frame. And then that means that machine, when it sees that frame calling, it sees its address and it reads that Ethernet frame in. And we're going to look at the Ethernet in more detail later as well. All right, so network 3 is the network layer. That provides the functionality for transferring data from a source to a destination, but having it go not just machine to machine on the same network. So Ethernet kind of works on just a local area network. In other words, here you have a node. This is a node. Here's another node. Here's a wire that connects them. How do you get data from just this one machine to this one machine? That's what Ethernet does. But if we're going to have that go from this machine to this one, to this one, to this one, to this one, and jump across a large network with a lot of connections, like the internet, then we need some other addressing information. So we need a way to deal with routing that and getting that packet and taking it from this node to this one at the hardware level, and then rewrapping it to go from this node to the next one at the hardware level, and then rewrapping it and go from that node to the next one at the hardware level. So that's where you can see that layered approach. The Ethernet packet contains this network layer packet. The network layer packet has the eventual address that the thing is going to. It also might be that the network layer has to do with segmenting and desegmenting that data. So for certain types of data links might have a smaller maximum packet size. So you have this large packet that came in or frame that came in, and you need to divide it up into smaller subframes and then put them back together on the other end when they go on to another kind of network. So this is the layer that routers operate within, and they transfer and route data through the extended network, not just one machine to the next. And the Internet Protocol, IP, is an example of that, something that sits at the network layer. And one thing is to visualize that layer as the postal system and mail carriers moving letters from point A to point B. So for example, when you drop something in the post office, they maybe sort that into a basket for a certain zip code. And that basket for that certain zip code, you can think of that kind of like a Ethernet. But then as it gets routed, it gets put on a truck. Truck is kind of like Ethernet. It takes it to the next sorting station. The next sorting station, they take the envelope out and they look at it and say, oh, this is for this to go on this truck. And it gets wrapped inside of that next truck and taken to the next location where somebody else looks at it. So they're constantly looking at the end destination and deciding who to route that to, where that data packet should go. Now, the transport layer. The transport layer is what provides kind of transparent transfer of data between end users. So in other words, the end user doesn't even have to know that they're packets. They just say, open this connection, here's a bunch of data. You figure out how to divide it up into chunks and then how to put it back together at the other end. And how do we do that reliably over a network that is inherently unreliable in most cases? Now, so that transport layer does all of the work for kind of sequencing things, having some sort of flow control, segmentation, desegmentation, error control. So in other words, dividing it up into packets, putting it back together, making sure no packets are missing, making sure no are duplicated, making sure they're in the right order, the same order they were sent and received. So in other words, you feed a stream into the transport layer, it'll handle the chopping it up, sending it, putting it back together on the other end, and then giving that same stream back out. So some protocols are state and connection oriented, meaning you make a connection. Once the connection's open, you talk. Other ones are datagram oriented. We'll talk more about that at a later point. But the idea there is that the transport layer can keep track of the packet sequence and then retransmit the ones that fail and discard any that it's already received. So the best known example of that would be the TCP layer in TCP/IP, which is responsible for converting messages into the individual datagrams and then putting them back together on the other end. Or you could use the UDP, which is User Datagram Protocol, where you're just sending these individual chunks of data yourself from the application level. Layer 5 is a session layer. You can think of that as the part of initiating and accepting and then ultimately terminating and closing down a communication of some sort. So that's responsible for managing the connection and terminating it when it's done. And that could provide either a full duplex or half duplex operation, but the idea there is it has rules in there for how do you start the conversation, how do you keep the conversation going, and how do you close it down when you're done. And notice that that would sit on top of that transport layer, which would sit on top of the network layer, which would sit on top of the data link layer, which would sit on top of the physical layer. Okay, now layer 6, the presentation layer, that deals with transforming data that in a way that provides a standard interface to the application. So in other words, you don't want to have a big Indian server talking to a little Indian machine and have the data get all corrupted because of that or be interpreted incorrectly because of that. Or you might have, for example, this machine has wants to compress that data and send it across, you want to have something on the other end at a layer that decompresses it so the application gets the decompressed version out. Or encrypt it on this end, decrypt it on that end so it's transparent to the application. And that's the important part of this presentation layer, is that deals with providing those services that involve kind of the format of the data, the encoding of the data, whether it's encrypted or not, and making that really transparent so the application doesn't have to worry about it. It just kind of happens. You feed data in, it gets encrypted, it gets segmented, it gets sent to the other end and routed, it gets then eventually put back together, goes back up through that stack, gets unwrapped, and then you have this decrypted data, and you don't even have to know how the encryption works or what it's doing. It's just doing it at this layer for us. So that layer's job is to convert to and from the format needed for the application layer, which brings us to layer 7, which is the application layer. And the application layer basically provides this way for the user application to access information on that network in some way. So that layer is the main interface for the users to interact with through the application. So there are protocols that exist at the application layer. So things like Telnet or FTP or SMTP or POP for mail services, or HTTP when you kind of access a web page and see it rendered in your web browser. But what that does is it allows the applications themselves to not have to worry much about what's going on below that. You basically just say, hey, here's this data I want. It handles that and passes it back up to the other end. But we still need protocols to send and process those messages. So HTTP, Hypertext Transfer Protocol, that web pages use, that the kind of World Wide Web was built on top of, those all are kind of application layer things, but there still needs to be a protocol there. You need to say, how do I request this web page? And when I get the response, how do I interpret that response? We need something to do that. But that's not deep down into the network and not built into the hardware. That's something at the application layer. And that's why something like the internet, you can do all these different things with. You can have a networked game that uses its own proprietary protocol. Or you can have FTP to transfer files. You can log into a machine remotely through a console interface. So you can connect and get some web page off of something. You can have a remote database connection that you connect to and do stuff through. There's just tons and tons of different things. You can have streaming music or streaming video that comes through in some way that might use one of these protocols. It might use its own protocol. Okay, some examples of things that are at each of those layers. I kind of created this list of potential protocols that live at each of these layers. So at the physical layer, we've got RS-232, which we've looked at before, and then a whole host of other ones, some of which you might recognize. A whole bunch of Ethernet variants here. POTS, plain old telephone system. If you have a dial-up modem, it might use that. Sonnet, DSL, and then we have the wireless things here, 802.11a, B, G, N, and then gigabit Ethernet down here, 1000 base TX. So pretty much anything that's doing the physical encoding. It could also be something more proprietary, like a wireless interface connecting a Mars rover to communicate to some satellite that's in orbit that communicates back to Earth. Data link layer, Ethernet is part of that. And notice these are forms of Ethernet, 10 base T, 100 base T, 1000 base TX. Those are all Ethernet variants. But Ethernet also has, since it has addressing associated with it, then we have that. Also 802.11, notice the variants of that at the hardware level, but then we have the Wi-Fi kind of addressing sitting on top of that. And then there's some other ones here, FDDI for fiber optic, frame relay, ATM, fiber channel, so forth. The network layer, the most common one that you see now almost exclusively is IP, but there are some other ones that are at that layer, IPX. ICMP, ARP. These are used for kind of lower level networking services, things not to route packets from end to end. And IPX was a kind of a novel networking system that is still used to some extent, but not as much as IP nowadays. And also transport layer as part of TCP, UDP, part of SPX. SPX was like the IPX version if you have an IPX, SPX network. This does the sequenced packet exchange. This does the kind of routing or internet packet exchange. But most days you'll have UDP, TCP sitting on top of IP. Oops. What happened? There we go. All right, at the session layer, we've got like NetBIOS, WebSockets, or just sockets themselves. Session establishment in TCP, session establishment in SPX. And again, remember the session layer is saying, think of it like making a phone call. There's part of that where it's the conversation, which is kind of the data, but then wrapped around that is the how do you start the phone call? Well, you have to dial the number, and then you have to wait while it rings. And so that's kind of establishing the connection and so forth. And then we've got the presentation layer. There's ways of encoding the data that are here that I added. And then the application layer is doing something with that, like a game server or a HTTP web browser / server or your email protocol for checking your email or transferring files or logging into a remote system or accessing a file system remotely. So in summary, this was a relatively short lecture today, and I want to give you time to look for that quiz and get that done as well. But the idea here, this is that layered model, like we said earlier, is often called the network stack. And you can kind of see why. It's all kind of layered, one thing on top of another thing. And the idea there is that data is going to be communicated by moving the application downward through the sending stack, adding the layers as needed, and then across a physical network, and then up as far as we need to move it to the next node. And then when it finally gets to the end, it goes all the way back up through the stack, unwrapping each of the layers as it goes, and until it gets back to the application. Now, in practice, in the OSI model, every layer has a very distinctly defined thing that the OSI model says this is what it's supposed to do. But in practice, there's some maybe missing layers here or there. There's some blurred lines between them. For example, TCP/IP, which is probably the most used networking standard in history for internet networking anyway. It follows this kind of layered model. But the OSI layers don't perfectly match because it's basically got the application layer and then TCP and then IP, and then that sits on top of something like Ethernet. So we've got like 4 layers there. And so there's multiple functionality of session and transport kind of wrapped together inside of TCP. And in Ethernet, you got the data link layer and the physical layer wrapped together inside Ethernet. So it's kind of things get combined together. And what we're going to do next class is we're going to take a deep dive into TCP/IP at a very low level and look at exactly how TCP/IP is organized, how it works, how it's set up. And we're going to look at the way that data actually gets wrapped inside of those packets from application to TCP to IP to Ethernet, and then unwrapped again from Ethernet to IP to TCP back to application on the other end. And rather than just talking about it in a more abstract sense like we did today in light of the OSI model, what we're going to talk about next time is going to be highly specific in what is actually inside of those packets. What do those packets actually look like? So when those are sent, like right now, there's probably, for most of you, there's a lot of mystery to that. For example, when you go to a web browser and you type in an address and some page comes up, and here, let me do that real quick. Let me put this where you can see it. So hold on one second. Okay, so here's a web browser. And when I go to this website and I type in /.org and I hit enter, and this comes up, how did that happen? What happened behind the scenes to make that happen? How did this request get made? How did it get fulfilled? And it might seem like magic now. Like, for example, you go to, I don't know, like Google. Oh, that went to Gmail. That's not what I wanted. Let's just go to Google. And there's Google. And I type in, I don't know, like Cookie Monster. And I hit enter. How did they get that request? How did they serve up this content to show these pictures? And it seems very magical, but really it's just sitting on top of that network stack. And the application in this case is the web browser. The protocol that this is communicating through is HTTP, or actually HTTPS in this case. You can see the little lock there that shows that it's secure. But HTTPS is really just an encrypted form of HTTP, but it's really very understandable for how stuff gets wrapped inside of a packet, and the packets get sent and they get put back together. And when they get put back together, they get unwrapped and interpreted according to the thing that they were wrapped with. And then you get this that shows up like this. Right now it seems very magical, but it's just data flowing across the network. Okay, so we're going to do a deep dive into TCP, IP, and Ethernet next time, which is what I said there. We're going to dig into those things. And then the class following that, we are going to actually start writing some code that actually talks over the internet. So we're going to write some TCP, IP code and learn about that. And then we're going to, in subsequent classes, learn about some things with TCP, IP. For example, how do you make a web server that talks HTTP over that? How do you make a web browser? And we're not going to write a full web browser like Chrome or something like that, but we are going to connect to a web server, download some data from that web server. And we're also going to create our own web server and connect to that and have it serve us some data. So that's where we're going in the coming couple lectures. So look for that next time, and remember to look for that quiz on the course page today. And that's it for today. Everybody stay safe. I'll see you all next class. Don't forget about that quiz.